excited to share my very speculative thoughts about the entire pipeline of NLP. So olden day pipelines, when I was doing my PhD, looked something like this, with a lot of emphasis on supervised learning. Data set you make once and it's there. It never just disappears or become out of fashion. The current day, it seems we have a lot of pre-training going on as well as a few sharp prompting going on in the field. So many papers around that. And then we do see relatively less of supervised learning. I do think that we're going to see this sort of a trend more and more, and then a lot more emphasis on the data set and evaluation. And then I would love to see more of these unsupervised approaches. And then a lot more other components such as reinforcement learning, continual learning, interactive learning, as well as knowledge models as a thing, which, by the way, has been alluded by Mark's earlier talk as well. And then decoding algorithms. Again, reasoning inference algorithms that we didn't worry as much about with the supervised learning or even few-shot prompting, but they can be really powerful, especially addressing logical inconsistency problems with the neural models. So, about evaluation, let me briefly highlight some such work in recent years. For example, this MEV paper at NeurIPS tried to address model-based evaluation approach for comparing human text and machine text, because it turns out humans no longer necessarily know how to evaluate GPT-3 text when it's so compelling. And then another line of research is try to look at how do we even evaluate the data set's difficulty in a more information theoretic way. So not only we evaluate models, we are now entering an era where we might actually want to evaluate data set or even evaluate evaluation metrics being meta on the evaluation itself. So a lot more activities toward that. But I move a little bit faster here because I actually want to talk about something else in this talk. But data set cartography, I think it was mentioned in Barbara's talk. It was about, again, evaluating on the data set as opposed to model itself. I would like to also highlight Clip Score at NLP last year, which was about evaluation on evaluation metrics. And then we discovered that, in fact, model-based evaluation, even without human reference at all, can actually do better than our familiar Blue Rouge or some other variants developed for image captioning cases based on n-gram statistics compared against the human written captions. So, if you think about it, that's a more natural way of doing it for humans evaluating image captions, in the sense that I don't need your human captions for me to judge whether an image caption generated by machine is good or not. I have my own understanding about the image caption, and so I don't need the references, and we are entering a strange era where it's becoming more of the case. But let me also highlight a little bit about reinforcement learning. Up until last year, I used to think that reinforcement learning is only cool for other domains except for language, because we seem to hear about AlphaGo or protein folding and all these other things where reinforcement learning is being truly amazing, groundbreaking, whereas we don't seem to hear as much impressive empirical results coming out of reinforcement learning. So that's what I used to think for a while. I'm beginning to realize that that's because the way that we were setting our supervision training, input-output pairs in a very particular way, we're not really permitting really great opportunities for new learning paradigms to actually show improvement. So I think those things will change. Here's one work that we tried to do RL for NLP, because a lot of reinforcement learning literature coming outside the NLP field tends to use language for RL as opposed to the other way, but we want something for NLP, so that's what we do. And in it, we developed a new algorithm called the NLPO. If you happen to be familiar with the PPO, that's a language-customized version of a PPO that will operate much better for language problems. And if you happen to be familiar with the nucleus sampling, the same idea is being used for that. Lastly, Quark. This is our new NeurIPS work for unlearning, so you don't want to just always start from scratch, which is the mindset of supervised learning. You just start from the scratch. Whereas for human bias we have about racism and sexism, we don't start our lives from scratch again for that. We just learn what's potentially aggressive toward other people and try to respect that. And so we can learn to unlearn. And so we can do that, and in doing so, it turns out reinforcement learning does provide a powerful paradigm because we may not have input-output pairings anymore. Rather, we have a reward network that can guide our learning. Okay, so that's the mandatory beginning speculative things, but in this talk, I want to focus on this two-part, knowledge models and unsupervised decoding algorithms, and how that's relevant in this today's situation, which basically is about David and Goliath, the art of leaderboarding, when we may not have extreme compute that tech companies do have, and can we do impactful research in the context? So we can draw inspiration from all the classical literature, such as The Art of War, which says, know your enemy, choose your battles, and innovate your weapons. We need to reinterpret that in the new modern deep learning context, which might mean that evaluation with realism and scrutiny, especially adversarial out-of-domain distribution and generative evaluation, where it's not about multiple choice, but machine has to generate answers. That's when machines tend to fail, by the way. Choose your battles with new tasks, harder leaderboards, and then also innovate your weapons through algorithms and data. So in this talk, there are many ways to address this, but I'm going to primarily focus on two things: symbolic knowledge distillation, and there are going to be a number of different case studies, and then decoding algorithms. Some of you might have seen the first thing, which is this causal common sense models, symbolic knowledge distillation. How many of you might have seen this before? Oh, not so many, so that's great. So the premise of this work is that language models are not knowledge models. We tend to use language models as if that's knowledge models because that's the best thing we have. But I think the only reason why that's the case is really because the tech companies are trying so hard to scale up their language models, whereas the community, NLP community at large, are not investing, the same level of effort into building knowledge models. So in our earlier work, we studied with this atomic at Comet, which are basically symbolic common sense knowledge graph, a bit more similar to maybe textual entailment graph from Mark's group. And then neural common sense model, which is built on top of atomic, because that way it can generalize much better for previously unseen examples that these models need to deal with. So graph is built only so that the neural models can train on top. And importantly, up until 2 years ago, I used to think that this graph has to be fully human annotated in order to be any good, because anything open IE-based method may not be able to produce good enough of a resource. So we had a follow-up work called Comet Atomic 2020 as well. And let me give you a concrete example, just in case you haven't seen before, what this graph looks like. So imagine you get your cars repaired, or X gets X's car repaired. Because as a result, you might want to call Uber or Lyft for a ride. You need to pay the bill. Beforehand, you need money, mechanics. So these are sort of like preconditions and post-conditions of the events that you need to deal with. And then there are some object-centric knowledge. For example, money can be used for paying for repairs. But if you really wanted to, you can also forward that into origami. I've never tried that, but this says something about stereotypical use cases as well as just object affordances based on naive physics knowledge about how the world works. And then finally, there are cases in which the center event cannot happen. For example, if you get your car completely totaled, then you cannot get your car repaired. So there are counterfactual contexts in which the center event cannot happen, and so forth and so forth. So we annotated it. We wanted to go pretty crazy with this. So the graph 2 years ago was about 1.3 million common sense if-then inference rules over 23 different edge types or relation types or inference types. So some of these are about causal common sense reasoning. Some of these are about object-centric, naive physics knowledge. But anyhow, again, fully annotated. So what good does this provide is that compared to our Comet versus GPT-3, which is so large, it doesn't even fit into the slide, GPT-3 is more than 400 times larger than Comet, which is trained on this graph, whereas GPT-3 read random web text. In terms of the accuracy of common sense inferences, so here the input to the test, the model, is a particular event, and then inference relation type, and then the model has to produce what might be plausibly true. So this is hard to game. GPT-2 off-the-shelf used to be very bad at this. So 36% of the output was any good. Whereas GPT-3 made a huge jump. This is very impressive. We'll get back to this. But Comet is significantly smaller and yet much better. So it does give you some sense of the power of data, especially in this form of a symbolic knowledge graph, what it can do even with the smaller models. So we put these resources out, and people all around the globe do very creative things. So we wanted to improve the resource further because it's really impossible for any 2 or 3 papers can actually build a resource that's forever good enough. So we now resorted to GPT-3 because the performance was shocking for us, but it's just so large, it's almost useless for anybody's computer. So we wanted to make it much smaller, but way better. So is that even possible, though? Because the knowledge distillation literature says usually it's the opposite. Well, it's going to be possible because we're going to do something pretty strange, which is that that funnel is actually a convoluted one. I'll tell you a little bit more in a bit. But compared to this more conventional knowledge distillation due to hint nettle, in which if you have a teacher model, you want to compress it down to student model by optimizing this cross entropy between the teacher output and student output. We're not going to do that here because, first of all, teacher model is not even common sense knowledge model. It's something else. And we don't want students to be just yet another language model, but rather we want a model of a different type, which is called a common sense model. In addition, the original research was sort of assuming that the output space is classification, whereas in our case, we want it to be generative models of common sense. So computing this exactly would be impossible, but that doesn't matter because everyone does sampling and call it a day. So we do that. But nice byproduct of the samples is that you can connect them up as if they are symbolic knowledge graph. In doing so, maybe I should go back to here. In doing so there was a critic model sitting that I'm going to mention in a bit that makes a huge difference because without critic, it doesn't work as well. So what we do is basically can be summarized in this graph. So here, y-axis shows the quantity of knowledge that is in the particular data set. So Atomic 2020, with respect to only a subset of common sense knowledge, 7 items, 7 inference types, was less than 1 million pairs. So Atomic 2020 had less than 1 million. Atomic 10x, if you just use GPT-3 as is, then you can generate so much so that now we have more than 5 million, getting close to 7 million different knowledge, but the black portion is bad. Green is good, black is bad, meaning you might remember it was about 73% of the time, meaning about 30% of the knowledge that GPT-3 generate is not good. So what do we do then is we train a small critic model. It's based on Roberta, it doesn't matter what exactly. And what we did was human annotation on about 10,000 examples, whether it's correct knowledge or not. Of course, this critic model doesn't know very much about common sense, so it's not very good at precisely classifying whether a knowledge is correct or not. But what it's good at is at least getting rid of a lot of bad stuff. So you see, we lost so much of a good portion, but at least it got rid of a lot of bad portion, to the point that now the accuracy or human agreement on machine-generated text looks better than Atomic 2020. So this is an entirely new situation in which now, comparing human versus machine in terms of accuracy or scale, value, or diversity, even diversity, it turns out GPT-3 is more creative and diverse when measured in many different ways. I'm here just showing a unique 1-gram count, but in the paper we report a lot more. So all around, machine-written symbolic knowledge graph winning over human-written one in all criteria. So this was a little bit like, this is so unexpected. But anyway, so that also leads to better models in general. It turns out we can also compare models trained on different kinds of knowledge sources. So GPT-3, again, was about 73% good. But if you train student model using raw GPT-3, somehow students gets better on its own. I'm not sure why exactly that case. But it wasn't as good as the human written atomic providing as a training data for COMET. But finally, if we use this GPT-3 plus Critic, which together makes a product of teachers that are becoming more critical, then the final COMET does better. And again, this says something about how the larger the better is not the case, because the final teacher actually used a lot less data than this teacher, loose teacher, which used a lot more data. So quality actually matters a lot more than quantity of the data. So after this work, we actually wanted to try something entirely different. Just in case you really couldn't care less about common sense, maybe sentence summarization. How about that? So this is our new EMNLP paper, where it's a reference-free sentence summarization, because we don't care about human written summary examples anymore. We're going to go reference-free. By the way, in the meanwhile, the new paper from UT Austin says, well, GPT-3 is the best summarizer. Forget about your supervised summarization model, which is maybe depressing, depending on how you look at it. Or maybe it's exciting, because maybe you can do this symbolic knowledge distillation again. So what we're going to do is we're going to grind this GPT-3 and then make it not only smaller, but hopefully better. This filter is where we can be creative and do different things. So in this particular paper, we have 3 different layers of filters. It's almost like a water filter in your house. You know, probably it's a good idea to have different layers of filter. So fidelity filter is based on NLI, the natural language inference model, in particular Wang-Li that I'm going to talk in a bit. And then length filter, because GPT-3 doesn't compress very much sometimes, so we don't want those like non-summarized cases. And then information bottleneck filter based on information bottleneck principle. But anyway, the quick summary of how this goes is that we then realized we don't have to do just one-time symbolic knowledge distillation. We can do this iteratively so that the future generation of teachers, the future generation of students can be teachers, a little bit like how academia works. So it turns out the students can become better and better. That's exciting. So the paper reports different types of evaluation, but basically we can improve the quality while not losing summary quality, but improve on other sort of aspects. So that's where things are for now. I kind of glossed over a lot of details because I wanted to share yet another entirely different example based on natural language inference. So this is going to be about data set. So it's the quick summary of what happens with out-of-domain evaluation of your favorite NLI model trained on MNLI, that's usually the de facto standard data set, is that they don't do very well. It's like you ideally want to see something close to 100%, but in general, they're all suffering. So what we do, or what we show, is that Wang-Li, which is 4 times smaller than the original MNLI data set, can do better across the board, despite the fact that data set is smaller. So how did we do that, you might wonder? And you're welcome to try this demo at wangli.apps.alenai.org. It does usually do better than off-the-shelf other NLI models, including Biden defeats Trump, Biden wins. That's in Telmont, and otherwise it's a contradiction. So I got inspired by Mark's example earlier. So how did we create Wang-Li? Is that first of all, Wang-Li means 10,000s of reasoning in Chinese. I felt that there are just way too many English names in data sets. I wanted to just throw in different language vibe to it. And then our assumption for a long time was that, well, humans know how to write this data set the best. But the problem with human annotation is that they have artifacts. So it's reported by so many different words, which really encourages machines to latch on spurious patterns and pretend that it's learning to do the task while it's just learning to hack the data set. So what we do is based on this dataset cartography, which basically said that these ambiguous regions, they're the gem. They're the most important region for out-of-domain distribution. And so what we do is we use that idea in order to ask GPT-3 to overgenerate potential NLI examples, and then use this filter, which in this case is basically dataset cartography idea itself combined with human validation. And it turns out, it may be like a relatively simple idea, but this does lead to a much better data set because it combines the diversity that machines can generate as well as the human ability to truly understand natural language inference problems. By the way, I couldn't agree more with what Barbara said earlier about human label variation being an important aspect of future NLP. In fact, I would go even one step further, not to say the noise is not all bad, but actually, I personally think all the good stuff is where there's high variance for a variety of reasons, but maybe we can discuss offline. But anyway, let me do super briefly on this neurologic decoding because the last portion, genetics induction, is going to rely on that. So this work was NAACL Best Paper Award, which actually builds on our previous NAACL paper with very similar title. In this talk, I'm going to just share these two. This is neurologic something, doesn't matter. So neurologic, pair of neurologic papers. And the key idea is that we hear so much about how larger is the better, which is on this left side of the slide. But really, the classical AI was about search algorithms. It was a big portion. And in fact, even for AlphaGo, we couldn't go very far without this Monte Carlo tree search. And so search might be still important, especially in this era of large neural models. So that's a sort of the wishful thought we had. And relatively speaking, it seemed that compared to how much people talk about either prompt engineering or pre-training itself, people were talking less about decoding time algorithms, and then usually just defaulted to use either beam search or some kind of sampling. But I personally believe that this is where a lot can happen. And in some sense, the recent chain of thought paper, as well as a range of new papers in this space, says otherwise. So decoding algorithm can be really exciting place. And in this particular work, what we want to do is to be able to respect logical constraints on the lexical items in your output. And if you think about, like, I give you this conjunctive normal form as logic constraints for you to satisfy, and you have to generate a sentence that satisfies that, you do not need even a single pair of examples. You can do it right away with a pencil and paper, just you work it out, no problem. So maybe we can do that with machines as well, especially through search algorithms. And if we do that, nice thing is that it can take care of lots of different kinds of NLG applications where you might want to control the content of the output. So neurologic decoding in a nutshell is a search trellis. We're not going to go into this. It's too much. But I just say, especially with the time zone difference, I just briefly mentioned that the complexity comes primarily due to the fact that when you have this full conjunctive normal form to deal with, you have to check whether clause is satisfied or not, either reversibly or irreversibly. And that creates a bit of a complexity with the search algorithm. But it's very much doable for computer scientists. In fact, the first author, Shiming, is the undergrad student at UW, just got out of algorithm class, really good at this kind of stuff at the time of the paper writing. And then because neurologic decoding is not able to look at the future, so imagine your task is write a sentence with the 3 words, car drives snow. Very easy for you. If you ask a neural network to do that and then use a naive decoding algorithm, after writing I drive my car during it might want to say summer instead of winter, but because we want to deal with the snow, winter is a better choice because we can project into the future. So that's a very classical A-star search algorithm situation. And so we do A-star ask decoding though, because it's not possible to come up with admissible heuristics with neural language models when projecting to the future, which means we have to come up with some approximation, and the details are not very important, but we try the greedy look ahead, or beam search look ahead. I'm just being very predictable here, but also sampling look ahead. So these are pretty obvious things to try, and it turns out the detail doesn't matter too much, but in general, it's a good idea to look ahead. So let me highlight one. The papers together present a lot of evaluation, but let me highlight one simple task, common gen. So this is a task where given lexical constraints, you have to satisfy the lexical constraints in the output. Again, you can do this right away. So if you look at coverage, this is constraint satisfaction coverage. The higher, the better. And then x-axis is the model size. If you look at blue line, that's what we used to do with the sequence-to-sequence models through beam search or greedy search, whatever your conventional search algorithm you want to use. So the larger is, the better. That's the trend that we always hear. But it turns out if we have a properly written neurologic decoding search algorithm, then coverage is always 100% or close to that. Whether you use Neurologic on top of a supervised model or off-the-shelf unsupervised model, it doesn't matter. Reasoning algorithms can be that powerful. We don't really have to pretend that neural network somehow, through this large parameter space, some logical magic pops out. I don't think that's actually possible. And then in terms of rouge emitter, which do correlate with this particular task, again, larger the better for blue line, but if you have Neurologic, then it's generally much higher. So much so that unsupervised Neurologic outperforms supervised approaches. Not only that, unsupervised Neurologic on smaller network can outperform supervised approaches on larger network when using conventional beam search or something. So I do think that we might be collectively neglecting the power of reasoning algorithms. And then in case you might think, oh, but common gen sounds like a made-up task. We also evaluate on things like constrained MT, table-to-text generation, and stuff like that. OK, so I did that only because I actually wanted to do this, generics induction. This is yet another example of symbolic knowledge distillation. And what we wanted to do is that I wasn't happy about the reliance on GPT-3. I just wanted to do without GPT-3. But that's really difficult to think to even dream about when GPT-2 is just so bad. So here the task is to be able to generate some correct knowledge about a concept. So bicycle, bicycle may have 2 wheels and stuff like that. What we do is based on neurologic decoding in order to lexically and syntactically guide the GPT-2's output so that it looks like a plausible generic statement. Meaning, don't do storytelling, don't give me convoluted sentences, just give me one simple sentence. And then it says nonsenses like bicycles are also pedal, whatever that means. So GPT-2 is so bad, like, why are we even trying to deal with this? Well, because we're kind of curious whether we can actually beat GPT-3 using just GPT-2 if we do this kind of a symbolic knowledge distillation. So the paper is coming soon, like we're almost about to archive now, finally. But long story short, it looks something like this. So generics KB, which is based on mining web data through OpenAI style mining. And if you imagine just mining web text, people don't necessarily say generic statements for everything in the world, which means it will be noisy. So it was about 75% good. And also quantity-wise, it was not very large. If you pull from GPT-2, you can truly overgenerate. And with the help of Neurologic, accuracy is about 40% good. But with a critic, we can throw away so aggressively so that we now have a much smaller amount, but still larger than anything ever existed before, and then still much of a higher quality. And now the final question remains, which is, how do we compare with the GPT-3? Especially when it keeps getting better, by the way. Like when originally GPT-3 was much worse, but now red line is the GPT-3 instruct. Last time I checked, it's really impressive because precision recall curve stays around 80%. It's really impressive. But GPT-2 plus symbolic knowledge distillation, etc., can do even better, which is exciting result in the sense that maybe it doesn't have to be all about GPT-3 and 4 and 5. Maybe there are other ways to get there as well. So to close, actually, I do think scaling laws are for real, though, and the denial is futile. Because, I mean, the amount of common sense knowledge that GPT-3 somehow acquired just by mask prediction is phenomenal. And also, I just love playing with these models. However, I do think that scaling laws only explain the necessary condition, probably not the sufficient condition. It's very important to highlight the fact that it's not the sufficient condition does not mean that it's not a necessary condition, by the way. It's like most likely super important factor that we cannot give up at all. And GPT-2 had to be reasonably big enough. I don't think I can actually do the same symbolic knowledge distillation using GPT-1. So the scale is real. I want to say something about the current paradigm of deep learning again. So for a long time, it was either supervised or unsupervised. Self-supervised. And this looks really powerful for leaderboards, but it doesn't work if we are doing evaluation that requires model to generate output, like abductive reasoning, counterfactual story revision, all this fun stuff that we trivially do. Models still fail to do this, so there's something odd about it. And in fact, if you think about how humans do learning, then you cannot possibly imagine taking a deep learning class in which professor has no textbook, no lecture, and just give you a lot of multiple choice questions with the correct answer marked. And then you complain that I cannot learn like this. Then the professor gives you lots of Python code or some other language code that you've never seen before, and you have to self-supervise. And this mode of learning doesn't work for humans. And how is it that we are hoping that somehow machines are able to do that? I don't think that just works. I realize I used to think supervised learning when we did this all the time. Actually, let me skip to the next one. When the field had the supervised learning as a big portion, I used to think, oh, that's a natural way of doing machine learning. And then when I see unsupervised learning papers, I used to think, what an unnatural way of doing machine learning. Because all that there is maybe like clustering and some grammar induction that doesn't work as well as a supervised case. But now I'm beginning to realize that supervised learning is fundamentally broken because a lot of the tasks don't even correspond to input-output pairs nicely. It really forces us to define problems based on labeling, which I don't even believe that much anymore, especially even with a simple task like natural language inference. There are cases when you realize that I could do entailment or contradiction at the same time, even if it has nothing to do with my personal background. You'll be amazed at how many such examples actually exist that we are choosing to ignore because we are fixated about making it as a three-way classification task, no matter what. And so there's a lot more outside the supervised learning, and I would love to see a lot more less supervised learning of different varieties in the coming years. And in this talk, as a one way to get there, I talked about symbolic knowledge distillation, because in my mind, language models are not the same as knowledge models. We shouldn't just rely on tech companies to create even larger GPT, whatever, for that, and create our own potentially, because it's going to be smaller and better. Okay, I'll stop here and thank you.
Wow, thank you, Yejin. We could probably unpack that into about a 4-hour version, but any questions on the distilled version?
Okay, so maybe I can go to your last remarks, right? That I totally agree that this is not how we learn. We don't learn from 1 million annotated examples just to know whether the sentiment of this movie review is positive or negative, right? It's not how we do it. And there has been made the point that a much better learning framework is to learn from natural language explanations, and kind of many people are working in this direction. And to me personally, one of the impressive things of GPT-3 is that it actually shows us that you can learn in this way, right? Kind of if you think about it, initially what did we have? We had rules, manual rules. Okay, then we had some kind of supervised examples, and then we had deep learning, which basically works in the same way. But now kind of we have a different way of learning that actually kind of you can work from natural language explanations, and typically something that we didn't think was possible before. And of course now you also have like in context learning and all that. It's not clear how far you can push it, but do you think this is moving us closer to the natural intelligence and kind of to a universal machine that can actually solve different kinds of tasks? This is what we as humans can do.
Yeah, that's a great question, which is also somewhat philosophical. I believe that that's the right direction personally, because just supervised learning framework in the classical version, at least, is just so limiting in so many ways. The fact that GPT-3 does strikingly well with instruction-based few-shot learning also says something about the power of the data, because it's a little bit opaque what exactly they do. But based also on other research, actually my colleague Hana Harji-Sherji and others at AI2 have worked on natural instructions as well as natural instruction 2.0, also known as supernatural instructions, in which if you actually have such a data set where instructions are human annotated for maybe thousands of NLP tasks, and then train T5, much smaller model on that, then the model actually does better with a quotation mark, quotation mark, for previously unseen tasks within at least that data set split. The data is not really matching probably what GPT-3 was trained on, but it really demonstrates the power of data and also the power of reinforcement learning that they're also using internally because they want to incorporate human feedback. I also do think, when we think about how humans invest into education material, even though there's a deep learning paper, someone else writes yet another, or NLP textbook, maybe I should say. And I think it's a wonderful thing, and maybe that's sort of like what I think about the data set going to the future, where I allocated really a lot of real estate here. The exact portion, by the way, is up to my artistic rendition, of course, so I don't know what the magic portion is, but I do think that creating somehow different declarative description of what data, what task we want to deal with might be a really exciting future, as well as knowledge graph, as well as other kinds of annotation. As much as I don't believe in supervised learning, I believe in a lot of data, especially complex annotations, that allows us to maybe optionally train a little bit on such data set, but primarily for evaluation of hard tasks, such as what Claire mentioned earlier about document-level event understanding. If only we have such a data set, I'm pretty sure that GPT-X whatever will not work very well. It just deep understanding fails still on especially larger document.
Did you do a comparison when you have the critic, and before and after the critic? Did you do a comparison on the sort of inferential power of the two models? What I'm thinking is, if we say, simplification, that these big language, the LLMs, are mostly kind of memorizing a bunch of facts, and they do a little bit of generalization, quote unquote, on the sides, and that gives them a lot of error, so you kill that error, right? So you're losing some of that generalization because we assume everything it gets is true, right? And so you're losing some of its little micro-generalization, which is killing. That's what you get to the right there. Does it at the same time also improve the true generalization so it can do new things, or is it just killing out the error and just not doing anything more fancy?
Great question. So because I was moving so fast, here we just see the end data for the moment, but what we end up doing is training a neural model on top of that graph as if it's just linearized text strings. And so if we train model on top of cleaned data versus uncleaned data, and then test their performances on previously unseen common sense situations, because we always only test on previously unseen cases, then we do see that the generalization itself becomes better when the data set is cleaned. So here, this is showing without cleaning. The last bar is with cleaning. And here's actually one reason why that may be the case. So the way that this common sense is produced is through sampling. It's not based on beam search because beam search leads to degenerate text. So when they're sampling, and GPT-3 may or may not truly understand what I want, so it says things, and sometimes it's a little bit awkward. And it may be because of a randomness to it, or maybe it truly didn't understand the task. So it could be because the model didn't actually know the common sense correctly. It could be because the model didn't understand what to do with this prompt engineering, or it could be because the randomness just pulled out wrong data. So we don't know which is the case. Whereas if we train model on top of this common sense knowledge graph, somehow it seems to reinforce the correct style of language as well as the content of knowledge being more correct. That's very hand-wavy, speculative thing I could say about this for now.
Okay. I have more questions.
Yeah.
Thank you very much. My name is Mohamed Yaqub, one of the faculty here, but I am a computer vision person. So in computer vision, we care a lot about continual learning, where you touched on a little bit. You spoke about that. Maybe in NLP is a different story because in vision we have a huge change on images, video quality, and so on. So can you comment on that, the effect of continual learning for the NLP domain? But my real question is, maybe the larger the model, the better for the sake of continual learning. What do you think about that?
The larger models definitely do learn much faster on a new task based on much fewer examples. So that's just a given. They do have a much better generalization power over different domains. So I think that's why I think scale is never going away, even if we try to develop algorithms that can sometimes match the performance of GPT-3. Having said that, I think continual learning is not necessarily what I see a lot in the NLP field compared to, say, broader AI or robotics or even computer vision. When I mentioned that a particular phrase, I was imagining something like, oh, maybe a language model looks at images and then continue to learn through different mode of learning framework. And then sometimes it unlearns some of the things that it learned in the past that needs to be updated, and then keep going on just like humans through this life cycle of learning. And in that context, large models are probably better if you only want to compare simple transfer learning based on model size difference. But there may be other things we can do on top where we insert more reasoning or more different kinds of something else, like knowledge distillation, whatever else.
Thank you.
Yeah.
One last question from Mohammed.
Yeah, thank you very much. A very interesting talk. In one of the slides, you had a Chinese name for one of the data sets. So my question is actually related to that, not to that particular data set, but actually to somewhat the portability and multilingual aspect of the work. I don't know if you have thought about, okay, so you build like these large common sense data sets and so on, and you exploit them in very interesting and useful ways. Meanwhile, if you go to a language other than English, you can translate these data sets, for example, and you build like resources with them and so on. But there are also these challenges of, people talk about indigenous communities, for example, having different ways of knowing. And so it's not like a one-to-one mapping between, a set of, norms and ways of knowing and knowledge, and so on from one language to another. So if this work were to be done, for another language, what would be the types of challenges that you can imagine having there, other than, the huge amount of work that is invested in creating these resources? So that's part one of my question. The other part, very quickly, I don't know if you have time, but you talk about decoding algorithms, and I also I'm thinking about okay, does this translate right away to other languages? And we know that the structure of languages are different and so on. So I just had these two, Yeah.
Yeah, that's a great question. I think doing Wangli for Korean language might be possibly, especially these days, because they do have a Korean language models. But for other languages for which they don't yet have large language models to pull the data from, or even like MNLI data set in their case, then if we just need to rely on machine translation and have humans correct, it may be one reasonable step, but probably not as satisfactory. So I guess Barbara emphasized the importance of multilinguality as well as more resource-sparse situations being important aspect. And again, it seems like unsupervised method or not fully supervised direction is truly important. And like my personal hope about, especially just about NLI, is that I wish we come up with a truly unsupervised approach. That's not even relying on MNLI, but it's not trivial to think about how exactly do that for broad scope of entailment. The Mark's talk earlier about finding those cases from data was interesting, but yeah, this is an interesting question. About your other question about maybe the diversity of norms and cultural norms and their influence on language models, and I do think that especially when we worry more about these human level variation cases, high human level variation cases is where this is where things are more actually interesting and matter to humans, and so we do somehow need to find a better way to really support value pluralism. Because there's no one gold label. I used to believe that there's a true label for any language problems. I no longer believe that. I mean, look at reviewer number 2, who didn't understand my perfectly written paper because they have a different understanding, different interpretation. And oftentimes, it's very reasonable what they're worried about. So I started really believing that we need to somehow address the pluralism of really a lot of everything. And how exactly do we do that? It's an open research question. But part of it might be that we may need to get out of this supervised learning mindset where everything has to be input-output, and then everything must have a high human annotation agreement, because by definition, a lot of language tasks do not have a high human annotation agreement. Even for PhD admission, it's not the case the same university. I mean, every university goes for the same person. And that's a wonderful thing that we don't agree, so that diverse, students get to work on diverse set of problems. So,
wonderful, a great point to end up on. So thank you again, Yejin.